All right, so we're doing volume of solids of revolution notes. So a solid of revolution is going to be formed when a flat two-dimensional shape is rotated around an axis. Consider the flat region below on the left. When that region is rotated about the x-axis, the solid pictured below to the right is formed. This objective of this lesson is to learn to find the volume of the solid. So we want to find the volume of that solid formed. So what we're going to do is, much like when we found area under the curve, right? We made a bunch of rectangles, and then we said basically this is for area, from A to B, we're summing up the height of the rectangle. F of x represents the height of each rectangle, right? It changes depending on where the rectangle is. But remember, this really means F of x means the y value of that point, and the y value of that point is basically how high it is, right? So that's the height, times the width, delta x. So we said if we made that thickness of each rectangle, the width, delta x, that would be this, the integral is summing up all these areas, so that would be the width of each rectangle. This together would be the area of the rectangle, and this is summing them up. Now what we do when we do the integrals, we're summing an infinite amount of rectangles, and that's because we're allowed to make their width infinitesimally small. I can't say the word. But when we do that, our delta x sort of changes into a dx. This is part of the major idea of calculus, that we can make that width so small that it's essentially zero. We call that an infinitesimal. It's infinitesimally small. It's even smaller than delta x. It's dx. And so we're summing up an infinite amount of infinitesimals. Really, really small, essentially zero widths. And the integral can do that from A to B. So it's adding all of those rectangles up, and hence that will be the area. And it won't be an estimate of the area. It will be equal to the area because we were doing an infinite amount of them. Okay, so we're going to take that same idea now and expand it to volume. So if I take one of these rectangles, for some reason I often call it a slice, I think because my high school calc teacher called it a slice. And if we rotate this figure about the x-axis, we're going to first just focus on one of these slices. If I rotate one of these slices about the x-axis, it makes what we're going to call a disk. And it's got a volume. This is really a really thin cylinder. So quick review. Remember, the volume of a cylinder is equal to the area of its base, which is a circle, times the height of the cylinder. Or we can use a lowercase h. It doesn't really matter. So we're typically used to seeing them look like this, right? Our cylinders, where we've got our radius, and then we've got our height of the cylinder. Well, now we're going to make it really thin, and we're going to call it a disk, because a thin cylinder is typically referred to as a disk. So we're making the height really small, and we're turning it on its side. So now our height of our cylinder, we're using a little h. The height of our cylinder is that little thin thickness there, and then the radius is going to be here. All right, so that's essentially how we're looking at these as cylinders. So this formula is going to be important, just like our area formula from before. Okay, so if we take that slice and we calculate its volume, that would be one of those disks. If we add up all the disks from A to B of all those slices that we turned into disks when we rotate the slice around the x-axis, if we add all those up, we will get the volume of this solid. So that's what's going on here. So I have a better picture. I kind of pulled one of these aside, and we have a little bit of a better picture here. Remember, this is touching the curve, like wherever the curve comes down, that's f of x. So the distance from the axis of rotation to f of x will be our radius. So that's what this is here. That's how we get our radius. It's f of x minus the axis of rotation. Now in this case, the axis of rotation was our x-axis, so our height just happens to be, or our radius just happens to be f of x. Because minus 0, because this equation is y equals 0 at the x-axis. We're going to see what happens when we have a different line of rotation or axis of rotation. All right, so this is a nice, a little bit, I had to draw ahead of time to make it a little neater. The height of each one of these we're going to call delta x. So here's our volume formula now for one disk. Oh boy. We've got our pi, we've got our radius, right, that's that part, squared, times the height, delta x, right, that's that thickness of that slice. That's going to represent the volume of one of these washers. If we want to add all of them up, we're going to sum the integral from a to b, and our delta x now becomes a dx because we're going to add up all the infinite ones. So that would be the sum of all the disks, which would equal the volume of the solid. There's not much of a difference between these two formulas. The only thing is that pi is a constant, so we pull it outside the integral, and it will just come along for the ride when we integrate. That's the only difference. So this is really going to be the formula that we're going to use to calculate this solid. You got to be able to picture this stuff. And to me, this is where, like, the last unit here is where it gets to be a lot of fun. There's a lot of really interesting stuff. You have to be creative. Yeah, there's just a lot of fun stuff to do here. So this is the start of it. Now, this idea of doing it using disks to estimate, just like we did for rectangles for area, disks to estimate the volume. If we make the disks thinner and thinner and thinner, we get closer and closer to the exact volume. There's a great app that demonstrates this. So I kind of set up the situation we had here, and I was making a lot of disks, but let's start with only a couple disks, like maybe 8 or 9. All right, so this is that same one we were just looking at, and if I take and I rotate, you can see these disks here, and we stack them up, and that would be an estimate for the volume of this solid. Okay, I don't know how to get it back. Come on. To where it's oriented the right. Okay, but you can see this solid, and what I'm doing is I just wrote a volume formula for one of these disks, and then if I integrate from A to B, I'm adding up all of those disks. Now, of course, this is not an infinite amount of disks. You can see it's telling me the volume of this solid here is 15.7, but as I add more and more disks, you can see that the volume's getting more accurate. I'm just going to hold down the plus button, and you can see the surface start to smooth out. We've got lots of disks in there now, and this is the solid. I'm trying to find the volume of this solid here. I wonder if you could change the color. I'm not going to worry about it right now. So there's our solid. That's what's going on here. All right, so again, what we're really doing here, just to be clear, is we're doing this formula, volume equals pi r squared h. So when we look at it this way, and then the integral is adding them up. So here's our pi. Remember, this is our r squared, and this is our height. The width is dx. All right, so anything else I want to mention before we move on here? We didn't have a function for this curve, so we can't actually calculate its volume. All right, so notice that the x-axis is the axis of rotation, and it's also the bottom of where where our area goes until. But we can move either one of those two lines. So in this case, we're going to pull up the bottom of the solid a little bit now, the area, and we're going to say that there's this line y equals c that you can see I put in here. And we're going to say, what about the area if it stops at C? All right. Oh, yeah, the one thing I wanted to say up here, this up here is our disk method. Okay. Now we're going to look at what happens down here. We can't use a disk anymore. Let me charge this up. When we take a slice and rotate it, let me make a slice here. Do it in red. And I rotate it around. Remember, this is my axis still. The x-axis is my axis of rotation. I get not a disk, but what we're going to call a washer. It's a disc with a disc in the middle removed. So, first of all, the picture we're thinking about, like, I'm going to go back to geometry here for a second. You were asked probably in honors geometry, I'm sure they asked you to find the volume of a cylinder, but then they would give you one like this where they'd say it's a cylinder with another cylinder removed out of it. Find the volume of that. So a quick review or rundown on how we did that. I think we would call this radius here little r, and then maybe this radius here big R. And so we could do it. There's a couple ways you could go about it. You could find the area of this right here. We call that an annulus by doing pi big R squared minus pi little r squared, and then take that area and multiply by the height of the cylinder, and that would be our volume. And we know that if I distributed the h to both of these, that's okay algebraically. And that would lead us to, this would be the other way that we could do it. This formula is taking and finding the volume of the outer cylinder without the hole removed. This is finding the volume of the inner cylinder, and since it's subtracting the inner cylinder, it's removing it. So we're going to do that same idea, but once again, we're going to really shrink our h down to be a really small height, and we're going to call it delta x because we're going to turn it up on its side, right? So that it's something like this. Okay? But again, what's going to happen here is our radius now, our big radius of our outer function will be that height, and we have this axis of rotation, right? And then our little radius will be this height here, and then our width will be here. So I took the time to kind of draw a little bit more of an exploded picture down here. And this is going to be called the washer method. It looks like a washer if you've done any kind of nuts and bolts and washers, right? That's why they're calling it a washer. So the capital R is going to be the outermost radius, which will be the radius of the big cylinder, and the little r will be the radius of the inside cylinder. And we want to do the volume of the big cylinder minus the volume of the little cylinder. Okay, and there's a couple ways we're going to attack this. So first of all, when we look at our radii or whatever, here's our axis of rotation. So if we go from the axis of rotation up to the outer curve, because there's going to be always an outer and inner curve. When the axis is not touching the edge of our region, we're going to have an outer curve and an inner curve. Our capital R is going to be the outer curve minus the axis of rotation. And then our little r is going to be, right here, the inner minus the axis of rotation. Okay? So essentially, again, I kind of drew this over here, and capital R I didn't want that to be that dark, but capital R is going to be the outer. That's our big radius of our big washer. It's not going to be the top. We're going to use the language outer for this. It's going to be the furthest away from the axis of rotation. So it's going to be outer function. Let me do this. I'll bring it over here so I can fit it. Outer function minus the axis of rotation. That's going to be the length of our big radius. The length of our small radius will be the inner function minus our axis of rotation. Alrighty, so the way we find that typically, that length will be like, remember that the function, go as thin as I can. Remember, this is come down and touching our outer function, and then this is like, in this case it was a straight line, that's our inner function. Right, so the capital R, like I said, that length is gonna be from f of x down to the axis of rotation, so I'm not gonna keep repeating it. So here's the volume. I'm starting to be like Khan Academy repeats things like a million times. All right, so essentially this is our formula. Let's see where it comes from. Let's look at the parts. So what we want to do is to find the area of one disk. Well, okay, we're going to sum up all the disks. And the volume, of our outer disk is going to be pi capital R squared times our height, which we'll call it dx here. Not a good idea. I'll use delta x. So we're going to just do the volume of one washer. It's going to be pi times capital R squared times delta x, because that's the width, right? And then minus the inner disk, and that's what creates a washer because we're taking out the inner disk, is pi times little r squared times our height, delta x. Notice that we can factor out a pi, so we'll have r squared minus r squared, and we can also factor out our delta x and leave it at the end. And now, because we said our r is our outer function, so this is going to be outer function minus the axis, and then minus the inner function minus the axis times delta x will be the thickness that we factored out. That's the volume of one washer. If we want to add all those up from A to B, we can pull the constant pi out. This will be the volume of the solid. I'm going to have my outer function, I'm just going to call it OF for now, minus our axis squared minus our inner function minus our axis squared, all of that dx. That integral will calculate the volume of the solid from A to B. All right, so that's kind of the parts of where this comes from. That's our volume formula for washers. This is our volume formula for disks. Okay, and the difference is when the axis of symmetry is also the edge of the region. So if I take this guy, and now I'm going to make it go only to, say, 0.5. Okay, so now you can see this is what we're talking about here. I stopped the thing short. And now if we look at this region, right, this solid, it's got a cylinder removed out of it. So that's why we have to subtract that inner cylinder. Okay, let's take a look. Where are we here? 19 minutes. Okay. Done a lot of explaining. I'm trying to get you to understand the formulas because you're going to need to know on the test. Like, they really can screw with you here, and you have to understand what's happening. So you got to decide if it's disk or washer. You got to know the outer function, the inner when it's washer. We're thinking about what's the length of the radius, what's the formula for volume. So got a lot going on, but let's just try to go after it now. Let's try to do some. So we got our formulas. All right. If the axis rotation and the parallel axis integrating needs to be in terms of x and limits of integration, you can pause it and read that. I'm not going to read that to you. I'm going to talk about it as I go probably. But so here's our region. They give us the two equations. Right? That's y equals, okay, this guy is dead. That's y equals x plus 2 on top. and y equals x squared on the bottom. Let me pause this so I can charge the pencil. Okay, we're charged. Okay, so find the volume of the solid formed when the region is rotated about the x-axis. So if I rotate it around, let's try to get a look at what's going to happen here. This thing's going to end up down there. This thing's going to end up way down there. The curve comes down here, comes back out there. Okay, so this is kind of weird, but that's what the thing will look like. So on the outside, it's like a lampshade, but it's going to have this like pretty flat but then steep point that it comes to inside there. And on top, it's going to have a little bit more of a, it's not going to go as steep. It's going to have a funnel. I almost think like, you know, like a tornado or something, a hole on the top. And those 2 points, the funnels, will kind of meet in that middle there. So that's what the volume's going to look like, the solid's going to look like. We're going to find its volume. Now, this is going to have to be a washer method, because if we're rotating around the x-axis, picture a slice. When you rotate it, there's going to be this can get ugly, but yeah, let me try that again. I shouldn't have put that line in there. That makes it confusing. The best I can do. But there's going to be a hole in the middle, so it's going to be a washer, which means I got to do the big radius minus the little radius, okay? Here's a look. I did change the colors. This has a lot of rectangles, so it's an estimate. This is the area we're looking at. If you look at the top, if we zoom in, you could see that like tornado cone thing I'm talking about, funnel in the top that goes to a point. You don't see through it though. It just touches on the other side. Let's see if I can zoom out. There's a much flatter, wider one here that's going inside. All right, and then if we make it many more discs, make it more smooth, and it's already telling us what the volume is, so we can see what answer we should get down there at the bottom. But if I zoom in, now you can see that funnel again up top, right? It comes to a point, and it's just touching. It's closed. It's touching this other funnel on the other side, which is much kind of like wider and shallower, and just kind of goes in right at the end. All right, so it's like a lampshade with these 2 funnels on either side, essentially, just to give you a visual. Okay, so let's find the volume. So since we're doing washer method, we got to punch out the middle, right, of each washer. So that means it's going to be the volume is going to be equal to pi from -1 to 2. And now we need the big R squared. So the big radius, right, if this is our axis of rotation, we're going to go from the outermost function down to the axis of rotation. The equation of the axis of rotation is y equals 0. The equation of the outer function is y equals x plus 2. So our big radius is going to be x plus 2 minus 0. And now we're going to subtract, and we're going to square it because we're doing volume, pi r squared. Okay, that's the area of the base times the dx. There's our width to get our volume. Okay, minus the volume of the inner guy, or the smaller part, the inside. And if I look at the picture, that radius will be this distance here, which is the inner function to the axis of symmetry. And this equation is y equals x squared. So the small radius will be x squared minus 0 squared. We're going to integrate that thing. I'm going to say let's practice integrating without our calculator. See what happens. So from -1 to 2, let's simplify. We got x plus 2 squared minus x to the 4th dx. Why does this feel like, I don't know. Pi times the integral -1 to 2. We got to multiply this out. It's probably the easiest way since it's only squared. So we've got x squared plus 4x plus 4 minus x to the 4th dx. So now I can do power rule. pi times x to the third 1/3 plus x squared, and that's a 2, plus 4x, and that's an x to the 5th minus 1/5. And we're going to go from -1 to 2. So we're going to do capital equals pi times capital F of 2 minus capital F of 1. So that's going to be pi times capital F of 1. We're plugging in capital F of 2, we're plugging in a 2, 1/3, 2 cubed plus 2 times 2 squared plus 4 times 2 minus 1/5 times 2 to the 5th minus, you got to put all this in parentheses, we're plugging in a -1, so 1/3 -1 to the 3rd plus 2 times -1 squared plus 4 times -1 minus 1/5 times -1 to the 5th. You can pause the video and take it from here. Welcome back. I'm getting 82/5 pi. Right, so if I go 82 over 5 pi, 51.5. And this guy's telling me it's 45.24. And it doesn't look like it's getting any bigger the more, right? That's as high as it goes. All right, so let's see here. Let's come on back here. Possibly I made a mistake in my computations, or that calculator is just not accurate enough. I'm going to pause it and check my calculations. I'll be right back. Found the mistake. I did my calculations wrong. 105 minus 33 is 72, not 82, which is that decimal that it worked out to be. Okay, so let's carry on. Find the volume when the region is rotated about the line y equals 4. So now this is not our axis of rotation. We're going with the line y equals 4. So now let's picture our slice. When I rotate it, there's still a hole missing. So it's going to be washer method again. All right, so let's look at how we do this. It's going to be washer. So the volume is going to be pi, and we're integrating again from -1 to 2. And this time for our radius, it's the outermost function is the x squared. That's the one that's furthest away from the axis. So our big radius is going to be x squared minus our axis of symmetry, which is 4 squared, minus our little radius, which is going to be the x plus 2 minus our axis 4 squared dx. So once again, we'll simplify and we'll practice doing this by hand. So volume equals pi. See if I can get this one right. Pi, and then the integral from -1 to 2. We're going to multiply this thing out, so we're going to get x to the 4th minus 8x squared plus 16. And then minus, if we, this is really what, x minus 2 squared, so if we multiply that out, it's minus x squared minus 4x plus 4, and that's dx. Simplify a little further. Our x to the 4th is the only one we have. We've got a negative 8x squared and a minus x squared here. So it's going to be minus 9x squared. We've got plus 4x here, because we've got to distribute that negative sign. And then we've got a 16 minus a 4, so we've got a plus 12. All right, so we're going to find our capital F of x is going to be pi times x to the 5th, 1/5. Okay, and you're going to take it from here. And you're going to evaluate it from -1 to 2 and see if you can get the correct answer. I'm going to pause the video and put it in the little app guy so we can get a look at the solid that's formed and see if we got it right as well. All right, let's go. Get everything set up. Find the volume when the region is rotated about the line y equals -2. So now, if our line is down here, y equals -2, I take a slice and I picture rotating that about the line y equals -2, and I'm going to get a washer because there's a big hole in the middle. I don't know. Try my best to draw this thing. There's a big hole in the middle, so it's a washer method. So it's going to be big radius squared minus little radius squared. So we're talking about washers here. So our volume is going to be pi from -1 to 2. Let's see. Our big radius is going to be the outermost function minus the axis of rotation. So it's going to be x plus 2 minus our axis of rotation is -2 squared. Minus our small radius, which is going to be x squared, the innermost function, minus our axis of rotation squared, dx for the thickness of our washers. That's the height of our volume formula. Alrighty, so if we simplify, we've got x, let's see, that's going to be a plus 4 squared minus x squared plus 2 squared dx. So we're going to multiply this thing out. X squared plus 8x plus 16 minus, you can finish this out. I want you to multiply it out, simplify the integrand, apply the power rule for integration, evaluate, see if you can get to the final answer. I'll get everything set up for us if we need to. Actually, I think I already have it, so pause it and do that. All right, welcome back. So let's look at our region. I adjusted, made the axis of rotation -2, so we'd get this thing. It's got a hole. This time it goes right through the middle because no part of the region touches the axis of symmetry. So this is like a, I don't know, a lampshade, I guess, with a rounded funnel taken out on both sides. But that's our volume that we're finding. This guy tells us that it's 101.789 approximately. If you do it out by hand and you get your exact answer, I got 162/5 pi. And that's the same decimal. So I'm getting 162/5 pi, which is about 101.788, I guess it was. Yeah, 789. Okay, so there we go. Let's try our last example. How much time do we have here? Where are we at here on time? 34 minutes. All right. So this will be about a 45-minute video. Known cross sections. No, sorry, we got to do this one first. Okay, now we're going to mess with you good. We're going to take this thing, instead of rotating it about, and we're taking different functions this time, but instead of rotating it about a horizontal line, we can rotate about vertical lines as well. All right, so I'm going to pause here I'm going to get everything set up so I can show you some pictures and stuff, and then we'll get going. Okay, so that app doesn't do rotation about vertical lines, so we're going to just have to picture this. I'll do my best to draw it. If the axis of rotation is the y-axis or is parallel to the y-axis, the integrand needs to be in terms of dy. So now we're integrating with respect to y. And the limits of integration need to be the y values. So now we're integrating on the y-axis, say from -2 to 3 or something like that. So we're going from, instead of left to right, we're going from bottom to top. All right? And then all of our curves need to be in x equals f of y format. They have to be functions of y. All right, so here's our curves. This curve is y equals plus or minus the square root of x. There's actually two curves. And the other curve is given as y equals x minus 2. So first of all, we're doing everything kind of inverted here. So our slice, this one's rotating, by the way, around the y-axis. So that's x equals 0 as its equation. If I rotate my slice here, it's definitely going to be a washer, because there's going to be that hole in the middle there, right? So we're doing washers again. Get rid of those. I'll just show a slice. So yeah, we're doing a washer method here, and everything's going to be in terms of y. So that means we've got to solve these equations for x. So if I square both sides, I get y squared equals x. Now that's written as x is written as a function of y, which is what we need. So let me clean this up all over here. We're going to call this curve x equals y squared. And if we solve this one for x, it's going to be x equals y plus 2. All right, so our washer method says we're going to go pi, and we're integrating from, let's see, a y value of -1 up to a y value of 2. Our outermost, because we have to do big R squared minus little r squared, so our big radius is the outermost function, which is y plus 2, minus the axis of rotation, which in this case is 0 squared, minus, let's see here, we've got our little radius, which is going to be like this guy here, which is our innermost function, which will be y squared minus 0 squared dy. Okay, let me just see, had this one worked out, make sure I have it right. Yeah, so this one I'm going to say, just to save a little bit of time and practice on our calculator, we're not going to do these by hand. Let's do these on the calculator. So even though everything here is in terms of y, when you're doing it on your calculator, you can kind of turn it back into x's, because the calculator needs everything in terms of x. So if I go into y equals, I'm putting in x plus 2, because I'm using the x equals y plus 2, right? Actually, you know what? Let's just do this. We'll not even put them into y1 and y2. It's probably just as fast to do this. We'll do f integrate. We're integrating from -1. Oh, we got to put a pi in front of there. Pi times the integral from -1. It's probably easier just to type it all out, to 2 of y plus 2 squared, right? So in this case it's x, because we're using x's again. I'm recording, right? I don't want to have to. Okay, yeah, I am. Y plus 2 squared. Yep, minus y to the 4th, or in this case we're doing x's here, dx. And we're getting 45.2 1.39. That is the volume of that solid rotated. So that would be units cubed. So yeah, everything's in terms of y. I had to understand that to set it up, and that got me these equations. But once I had these, if I'm using my calculator, I can just go back to x's, right? As long as I use these equations. Be careful not to use those, because you had to convert them. Whoa, I don't know what just happened. All right, so now let's look at this one. Find the volume when the region is rotated about the line x equals 4. So now, whoops. X equals 4 is this line right here. So again, our slice doesn't quite touch everywhere, the axis, so it's going to be washers. Let's see if you can do these last two on your own. I'm going to put the answer. So you're going to pause, see if you can set up the integral. I'll write out the integral, and then we'll check your integrals, and then you can go on and do them in your calculator and see if you get them right. Okay, so this would have been the integral that you would set up. So see if you got that right. Now you can go ahead and solve for it. Okay, welcome back. You used your calculator, and this is the decimal I got. This is the volume that I got for that solid. Now I'll pause the video again and see if you can set up the integral for the last one. Okay, this is the integral you should get. You can type that into your calculator now. You can use x's instead of y's, and see if you get the same answer as me. So pause the video and do that. Okay, welcome back. I got 152.681. And that is it. We got one more section, volumes of solids with known cross sections, coming up, and you are done with AP Calculus. We will just be getting ready for that exam now. Nice job, folks.